My name's David Mackey. I am the founder of Mbryonics, along with my brother and sister. We created Mbryonics in 2014. We specialize in satellite optical communication. We do both optics, photonics, and software for these key systems that are linking the next generation of LEO Earth constellations.
A few days before OFC, I'm interviewing some of the key leaders of the Optica corporate members that are making a difference in the world of optical communications. I'm speaking with David McKee, who is the CTO of Mbryonics. Mbryonics is a startup from Ireland making a big difference in free space optical communication. David, please start by explaining how your technology is different to names like now we know such as Starlink or OneWeb.
Starlink and OneWeb, they're two slightly different satellite constellations out there that are creating global networks. Starlink actually is relatively close to what we're doing in that they are also using these optical intersatellite links to make this global mesh network, whereas the next generation of OneWeb will include laser links. They don't currently include laser links. So what we do in Mbryonics, we do the actual satellite optical terminals all the way end to end to the ground station links that create these laser links from both space to ground and space to space. The core technologies that we address is overcoming the atmospheric channel, as well as really sending terabit per second class type data through these optical communication terminals, which is state of the art in terms of what is being achieved currently. In terms of what we do much better than everyone else, we do a very large telescope aperture, so we can send a lot more data with a lot less light. It's essentially so much more power efficient, which is critical for space applications, which are size, weight, and power constrained because they're having to run on solar panels in space. And because you're launching them into space, you have to have as low a mass system as possible. So look, these are the key sort of metrics that we try and optimize around. One of the core differentiators we have, though, is that we are interoperable with every other satellite optical terminal out there. So we've been involved in this Space Bacon program, which we'll talk a bit about, I'm sure.
1 terabit per second communication, indeed, that's very unique. The Starcom Optical terminal, the interoperability of this terminal is what makes you at the forefront. But how far have you got in scaling your product? When can telecom providers have one?
So we've been on the go now for 10 years. So it's we don't really consider ourselves a startup too much anymore, but it's been a long journey of development. So it's an extremely challenging technology from a number of different areas, both including, so we work on both integrated photonics and then the bulk optics of the system, to amplifiers, to the software stack that creates the networking. So it's a huge end-to-end product development intensity. So we will have our first launch next year in Q2 of 2026. So that'll be the first terminal that we'll have going into space. In terms of people who want to buy them right now, they are available, and we're delivering them to different customers. So we have one customer in Singapore called Spectral that we're doing a quantum key demonstration with them next year as well.
Indeed, David, you are not a startup anymore. You have been working both on optics and photonic integrated circuits for many years. We finally see peaks, photonic integrated circuits in space.
Yes.
Can you describe the road that you had to go through to make sure that you get peaks with the right reliability to put them up there?
Yeah, it's been a very long and challenging road. So there's been numerous iterations, both on the foundry side as well as on the PIC design side, and then there's the electrical ICs, and then the real challenge has always been, which across the industry, is the photonics integration itself. So look, we've worked very hard on the packaging and processes as well as the actual packaging design, both from a thermal perspective, electrical, and then the materials we use. And then look, the final things we tend to have to do, particularly for space, is then space qualification and reliability. So you put them through thermal vacuum chamber, radiation tests, and then life cycle tests is what you also do. So look, it's been a long journey of getting those technology readiness levels up, and we're very excited about one product we have in line is called Terabix, which allows for these interlinking of digital payloads in space. So it's very popular for use in digital beamforming type applications where they want to get lots of data from a central payload out to a large beamforming array.
Mbryonics recently secured a 17.5 million investment from the European EIC Accelerator. What are you doing with the money?
So we've been scaling up quite dramatically our production facilities the last year, as well as so we have two main sites, one in Galway and one in another part of Ireland, where we're building a huge factory, about 40,000 square feet. In terms of the one in Galway, we are doing our sort of initial production processes there. So we're getting to about 200 units this year per year of these satellite optical terminals. And then we're scaling up to about 2,000 units for next year is the goal on that front. And this is to deliver lots of terminals to these mega constellations from numerous different opportunities, from the SDA to Iris Squared to other different commercial opportunities that are out there.
But you still are gonna get your chips, your photonic integrated circuits manufactured in foundries. So what are really the goal of your manufacturing facility in Ireland?
So there's a lot of different challenges in these satellite optic terminals. The optics, so we are relatively vertically integrated. So apart from the photonic chips, we do pretty much all the other manufacturing processes, from the photonics packaging to the electrical IC packaging, and then the actual optical terminals themselves. We manufacture over 90% of the components that go into that, from the coarse pointing assembly to the mirrors that make up the telescope, to the actual fine steering mirrors and all the other subsystems, from even down to the camera sensors that we do, we actually make and assemble here in Ireland. So it's quite a large technology stack, and it's actually requiring a huge footprint of production facility and clean rooms to actually produce all these systems and test and validate them, which is the key for these space type applications.
For the ecosystem, in the last years, we have seen many OSATs in photonic integrated circuits, many packaging and testing facilities in peaks worldwide. It's not just only Fabrinet. There are, of course, smaller and bigger ones. We have, of course, like Fix in the Netherlands. So why did you decide to do the packaging yourself?
So look, our market has some unique challenges, particularly because we're going into space. So there's definitely different sort of design challenges around that, even from radiation to the thermal aspects. So obviously, look, normally in data centers and telecom type applications, you've got the atmosphere and air to dissipate heat. We always have to design things that they're either radiating away, or else there's thermal contexts that are well designed. So really, from start to finish of a whole system package design, you have to design it from the ground up for space. So it's always made sense that we would both develop then the packaging processes that go with that, as well as designing the package itself. And then even the materials we use have to be qualified for space. So look, it's every single aspect of it really has to be customized. While there's a shift towards using COTS type systems for space, it's still, look, the reliability and the end customer, they won't accept a 50% failure rate when these things are on orbit. They want 99.9% uptimes. That means it has to be radiation hardened by design, particularly if you're going to these higher orbits such as MEO and GEO, where the radiation environment becomes very challenging.
In datacom telecom, packaging is one thing, but the real expensive and time-consuming part is the testing. I assume it's similar to you, because you're actually taking a device and putting them in space, and failure has to be 0%. How do you do the testing of every single module? And especially, how do you plan to do it when you go to very high volume production next year?
So very good question. So we do different tests at different stages of the assembly. So obviously we do chip level tests before we even get close to assembling them. And look, we do have to test every single module. So we have a good unit test system once we get to the final assembly. And then we have to do burn-in, which is actually you put it through initial heat chamber cycles. So the numbers that we're actually having to sort of achieve are about on the order of 30,000 to 100,000 units per year for some of these applications. So it's a real scaling challenges. And this is why we actually sought the investment that we could deliver on some of these very large opportunities that we are involved in. So it's a massive market, much bigger than people may be aware of. It is, some of them are on the order of telecom size data center type units that you actually need to deliver. So it's a definitely a challenging both reliability and scaling challenge. So really focusing on the yield has been one of our core aspects of actually getting this system to be very commercially viable.
It is easy to replace a pluggable transceiver from a data center rack. It is much more difficult to make any adjustments once you put the device in a satellite. How are you going to deal with the fact that peaks still don't have 100% yield?
So yes, particularly on the photonics side of things, even the foundries, the yield, while it's getting better all the time, it still is a major challenge. So we have to do a lot of wafer level inspection, that we actually are sorting out the chips before we even get to the final assembly. So it's actually quite similar to the co-packaging optics challenge, where you're putting a lot of photonics in with your ASIC, and you look, all of those, if there's one that fails, that's the whole unit gone. You can't replace it once it's all assembled. So it's a very similar both packaging and reliability challenge that we're facing for the space industry. So look, it takes a lot of screening, a lot of testing, and a lot of process development that you're really getting that yield as reliable as possible in the actual photonics assembly part of the process that you're doing, which is not a significant challenge that we are addressing. Yeah.
Dave, the final question, the Optica question, what can other members do for you? and what can you do for them?
So we are out there to work with every other satellite partner, and there's numerous places where we overlap with people. So we are very good at photonics packaging. If you have a hard photonics packaging problem that needs to go into space, we offer a photonics packaging service and design engineering services around that. That's something that we are launching in a service called PackPick, which is a subsidiary of Mbryonics. In terms of areas where we want support from other people, we are out there looking for good suppliers of optics, radiation hardened electronics, the co-design of digital signal processing that goes with the data rates we're sending that are really, really challenging. So look, we are out there talking with every DSP provider, seeing if they can provide something that'll be more power efficient, and really anything that can improve the end-to-end data chain in space laser communications. So that can be digital switches, better thermal management systems. Come talk to us if you're working in the space industry, really is what we really want to talk to anyone.
Thank you very much, Dave, and congratulations on everything that you are building. Thank you so much.
Thank you, Jorge.